Hey everyone, let's just dive right into this. Welcome to today's Explainer. We are looking at something that is just truly awe-inspiring. We're going to take a journey deep into the Ara constellation to check out a massive, glowing cosmic structure known as the Fighting Dragons of Ara. But more importantly, we're going to look at the incredibly powerful engine that drives the whole thing, the stellar cluster Caldwell 82.
Here is our quick flight plan for today. We're covering 1. The Fighting Dragons, 2. Caldwell 82, the engine, 3. Meet the bully stars, 4. A rare magnetic anomaly, 5. Youth and mass segregation, and finally 6. High-speed galactic journey. So what actually powers the Fighting Dragons of Ara? I mean, when we think about the dramatic, sweeping, chaotic shapes of this giant cosmic vehicle, you have to wonder, what massive hidden force could possibly carve out a landscape like that? Just imagine the sheer scale we're dealing with here. You have this brilliant, glowing outer shell of the nebula. That's NGC 6188, or the Fighting Dragons. But behind those glowing clouds of gas and dust lies a really powerful driving motor. It helps to think of this entire region as a giant cosmic car. The glowing nebula, that's the chassis. But hidden inside is the engine, generating all the horsepower. And that engine is the open star cluster Caldwell 82, also known as NGC 6093. Section 1, the Fighting Dragons in Caldwell 82. Let's quickly run through the vital stats for Caldwell 82. It's located deep in the Milky Way, roughly 4,000 light-years away from us, sitting right inside the Ara constellation as part of the Ara OB1A association. But what is truly staggering here is its age. At just 3 to 5 million years old, with some very specific measurements pegging it at roughly 4.22 million years, this cluster is, well, it's practically a newborn in cosmic terms. Now, what's really fascinating about this young cluster is a concept called triggered star formation. You see, Caldwell 82 isn't just sitting there passively. It actually acts as a massive catalyst. It's embedded within an HI region called RCW 108. The immense forces pumping out of our engine compress the nearby molecular clouds. It acts like a giant shockwave that literally triggers the birth of even more completely new stars in the surrounding area. And when researchers mapped out the dust distribution using visual extinction data, they uncovered an incredible detail about how this cluster formed. It appears to have this outside-in formation history, meaning the stars sitting right in the core of the cluster are actually younger than the stars scattered out in the surrounding halo, which are estimated to be around 10 to 15 million years old. Star formation is quite literally propagating, rolling through the region. Section 2. Meet the bully stars. If we pop the hood and look right into the core of Caldwell 82, we see it is absolutely dominated by two massive O-type stellar systems, HD 150135 and HD 150136. These are the bully stars of the cluster. Their extreme size and their incredibly intense energy output completely dictate the harsh, turbulent environment of the whole region. Seriously, everything that happens in this nebula is pretty much subject to their whims. So how exactly do these bullies exert that control? Well, it comes down to 3 basic steps of stellar feedback. Step 1. These massive stars pump out incredibly intense ultraviolet radiation, which ionizes the hydrogen gas around them. Step 2. Their powerful ionizing winds push and shove the surrounding material, carving out huge cavities in space. And finally, step 3. As all that material gets pushed outward, it slams into nearby molecular clouds, compressing them and sparking the creation of brand new stars. They are literally the pistons powering the glow and the evolution of the Fighting Dragon. Section 3. A rare magnetic anomaly. This brings us to a really fun stellar oddity known as a hybrid pulsator. Tucked away within Caldwell 82 is an eclipsing binary system called HD 149834. Now, eclipsing binaries are already super useful because they let astronomers precisely measure stellar properties. But the primary star in this specific system is exceptionally rare because it's a hybrid pulsator, meaning it pulses and vibrates in multiple different ways at the exact same time. Let's compare what that actually means in practice. Usually, a massive star kind of pixeling. It'll either exhibit pressure modes or P modes, which are typical of beta Cephei pulsators, or it'll show gravity modes, G modes, which you normally see in slowly pulsating B-type stars. But HD 149834 does both simultaneously. This overlap is a phenomenal, totally unique laboratory for testing stellar physics. For example, just the fact that both of these pulsations are happening strongly indicates that the system has a near-solar metallicity, which gives us precise clues about its internal makeup. Section 4. Youth and mass segregation. 14 million, that right there is the relaxation time of the cluster, in years. But remember what we established a few minutes ago? The cluster itself is only about 3 to 5 million years old. So the really crucial takeaway here is that because its actual age is much less than its relaxation time, the cluster is what astronomers call dynamically young. Basically, it hasn't had nearly enough time for gravitational interactions to sort all the stars out into a stable equilibrium. But here is where we hit a wall, a massive paradox. Despite being dynamically young, the cluster exhibits significant mass segregation. This is the process where the heaviest, most massive stars sink down to the middle of the cluster, while the lighter, lower mass stars get pushed out toward the edges. And that's the big mystery. We know Caldwell 82 has a relatively low concentration parameter, which just means its outer structure is quite diffuse and spread out. Yet those massive bully stars we talked about, they're firmly parked right in the dense core. So how did they get there if the cluster hasn't had time to relax? Well, it suggests that this mass segregation might actually be primordial. It didn't happen slowly over time. The cluster likely formed this way from the very beginning, straight out of the molecular cloud. Section 5. High-speed galactic journey. 212. That is the staggering total space velocity of Caldwell 82, measured in kilometers per second. I mean, it is just flying through space at an incredible rate. It's a high-speed anomaly compared to a lot of its peers. And when researchers analyzed its orbit, they found a fascinating motion vector. This cluster doesn't just travel in a simple flat circle. It actually follows this really unique boxy trajectory as it navigates through the Milky Way. Let's break down that orbit a bit. Caldwell 82 originated within the solar circle, with a birth radius of about 6.83 kiloparsecs. It belongs to the Milky Way's thin disk component, and it reaches a maximum vertical distance of 173 parsecs above the galactic plane. But why is it moving at 212 kilometers per second? Researchers think this extreme speed could be the result of its specific location within the galaxy's rotation curve, or, amazingly, it could be carrying the momentum of past gravitational perturbations from nearby massive structures. It was essentially given a cosmic shove. Which leaves us with this final thought today. We have a high-speed, dynamically young cluster. It's got primordial mass segregation, bizarre magnetic hybrid stars, and dominant O-type bullies triggering rolling waves of star formation. So, what does the sheer mechanical complexity of Caldwell 82 teach us about the turbulent, violent, and beautiful origins of our own galaxy? It absolutely shows us that the universe is far from static. It is an active, roaring engine of creation. Thanks for joining me on this explainer, and keep looking up.